Good morning, dear student. Today we are going to learn the second lecture about the linear transformation. Myself Dr. R.S. Damur, and I am the assistant professor at LD College of Engineering. This is your second semester topic, linear algebra and vector calculus. The topic name is linear transformation. In our previous lecture, we have learned about the linear transformations, basic definitions, and some simple examples to check out that the transformation is linear or not. Now starting with this linear transformation. So in this chapter we again recall that these are the topics. First of all, introduction, which we have to done in our first lecture. This is the definition of a linear transformation, the null space and range, isomorphism, matrix representation of a linear transformation, and similarity. So these are the topics, and these two topics, first and second topic, we have to done in our first lecture, but up to the basic level. So this just recalling that, okay, what is the linear transformation? In our previous lecture we have to define the linear transformation. Yes, what is the definition of a linear transformation? Just recall that. How we define the linear transformation, from which set to which set. So we have to define the linear transformation T from vector space V to W, which is a function from a vector space V into vector space W. Then T is called a linear transformation from vector space V into vector space W if for all vectors U and V in vector space V and scalar C, it satisfies the following condition. If this, which are these two following conditions? Remember? Yes, which is this: T of U plus V plus T of U plus T of V. So what is this? This is known as the additive property. So two vectors in this vector space, image of this must be T of U plus T of V. So this is the additive property. So this transformation possesses the additive property. And what is the second property? Yes, recall. Just this. Yes. T of C into U, where C is scalar and U is a vector in vector space V. Then T of CU, this is C of C into T of U. So this is known as the homogeneous property. So there's two basic properties which we have to require for any transformation to be a linear transformation. So for this, you must check out this for a linear transformation. Now what we have to do this? We know this property. Say this: T of U plus V equal to T of U plus T of V. This is the additive property and homogeneous property. T of CU equal to T of U. But suppose I can make this two property as a combination of only one equation. So how I can write this as a C into U plus D of V. So I can take this two constant C and D such that their linear combination C of U plus D of V satisfy this. So this is C T of U plus D T of V. Clear? So this is the equivalent condition for this two condition, or you can produce this two condition from this condition. How? Suppose you can put down this C equal to 1 and D equal to 1. Then this is T of U plus V can be written as C equal to 1. So this is T of U, D equal to 1. So this is T of V. So which is my first condition. T of U plus V equal to T of U plus T of V. Same thing. Suppose I can replace this C as it is, but D by 0. So what becomes? C into U plus D into this vector 0. D into vector V. So D is 0. So this is whole becomes 0. So T of CU, this can be written as C T of U plus D equal to 0. So this term becomes 0. So clearly T of CU can be written as C of TU. So checking these two conditions separately, you can check out this condition as a whole, and directly you can say that if this satisfy, then the transformation is a linear transformation. Now again I have to say that this transformation linear transformation is an operator. Remember that. What is the operator? The transformation from V to W, but V equal to, suppose W equal to V, then the transformation is said to be the operator. Okay, so the domain and codomain both are same, then the transformation is known as the operator. Clear? Now just recall that what we have to do in our first lecture. Again we have to define the vector space, because in vector space chapter you have to define the vector space, because lots of many use of this vector space in this. So just recalling this 10 conditions: closure under addition, possess the commutative law, associative law, addition, existence of identity, existence of inverse, and for scalar, closure property for under multiplication, and distribution over scalar addition, C of u plus v equal to C of u, distribution over a scalar multiplication, associative of scalar multiplication, and existence of multiplicative identity. Okay, if these 10 conditions are satisfied, then we have to say that the space is a vector space. Okay, just we have to use this vector space, so we have to define this and recalling this. Now fastly we have to do this. Okay, which type of example we have done? We have done the zero transformation. What is the zero transformation? T from V to W, T of u equal to 0. Is it linear or not? Just recalling your previous lecture, yes, it is linear transformation. The identity transformation. How you define the identity transformation? T from V to V, T of u equal to u. Is this transformation as a linear transformation? Yes, it is linear transformation. And here see this W equal to V. Okay, so this transformation is nothing but this is an operator. So we have to define the zero transformation and identity transformation in our previous lecture, and which is linear transformation. See this dilation and contraction operator, T from V to V, T of u equal to Ku, where K is scalar. Clear? And again we have to prove that in our previous lecture that this is a linear transformation. So this three: zero transformation, identity transformation, dilation and contraction operators. Again what we have to do this? Again T from Pn to Pn plus 1, set of polynomials of order n and set of polynomials of order n plus 1, and we have to define this transformation T Pnx equal to x into Pnx. So we have to prove in our previous lecture that this transformation is a linear transformation. We also see this a linear transformation using an inner product space T from V to R, T of u equal to inner product u with u0. This is again a linear transformation. So these are the linear transformation which we have done in our first lecture. Okay, suppose this for matrices T from n cross n matrices to n cross n, and transformation of A is defined as A transpose. Again this is a linear transformation. Now suppose I have to define this T from R to R and Tx equal to x square. Is it linear transformation? Just you have to prove in your previous lecture that this is not a linear transformation. Now see this. We have to lots of do this examples. So how we check out this is the transformation is linear or not using the additive property and homogeneous property, or the combination of these two. But now the linear transformation has some properties. If the transformation is linear, T from V to W is a linear transformation, then it satisfies some property. Say this. What is the first property? Transformation of zero vector is again a zero vector. The first property. And transformation of difference of two vectors u minus v is written as transformation of u minus transformation of v. So if you know that your transformation is linear, then it satisfies this two property. Now just do this. How we prove this? T of 0 equal to 0. Say this. Let u is in V. Okay, any vectors in V. Okay, now V is a vector space. So it possesses the additive identity. There exists some 0 belongs to V. Additive U plus 0 equal to 0 plus V by the definition of this vector space V. So there exists 0 is also in V. Now the transformation is linear. So you know that it is linear transformation. Now 0 belongs to U, 0 belongs to V, and U belongs to V. So their scalar multiplication 0 into U is also in V. Okay. So scalar multiplication with vector is again in vector space. So this is 0 into U also belongs to V. So this is the closure property of scalar multiplication. 0 into U is also in V. Now what happened that 0 into U is also in V, and T from V to W is a linear transformation. So T from V to W is a linear transformation, so it satisfies the homogeneous property. What is the homogeneous property? This is your homogeneous property for any scalar multiplication with this vector. T of Cu can be written as C into T of U. So now what happened that by closure property we saw that this 0 into U in V. So this transformation T into 0U by this T into 0U can be written as 0 into TU. Clear? So now using this T of 0, okay, transformation of 0 can be written as T of 0 into U, this, which is equal to 0 vector, okay, and T of U by this T of U equal to 0. Clear? So this is T of 0 is nothing but 0. Clear? Now the second property. What is the second property? T of U minus V can be written as T of U minus T of V. So for this I have to take this two vectors in V. U and V is in V. Okay, two vectors in V. Now V is a vector space, so there exists minus V, additive inverse for this V, okay, also in V. Say this, any scalar multiplication of minus V is also in V, or additive inverse of V also belongs to V. So minus V belongs to V and U belongs to V, and their addition U plus minus V also belongs to V. So this minus V into V. Clear? So T of minus V you can find out this. T of U minus V, this belongs to vector space V, and transformation of this or U minus V can be written as U plus minus 1 into V. Clear? So as T is a linear transformation, this T is a linear transformation, so this is U plus this can be written as T of U plus T of this. Okay, and by scalar multiplication this can be written as T of minus 1 into V can be written as, I can take out minus 1 outside because this is a homogeneous property, so minus 1 into T of V. So T of U plus T of minus 1 into V can be written as T of U minus T of V. Clear? So it satisfies the second condition also. T of U minus V can be written as T of U minus T of V. Clear? So if T is a linear transformation, then 0 vector transform to 0, and difference between these two vectors can be written as T of U minus T of U. So transformation of difference of two vectors can be written as transformation of U minus transformation of V. See this. Now see this, some more example, but in previous example what we have to do this, we have to use the generalized vector space V to W. Now we have to use the vector space from Rn to Rm. Okay, and now we have to check out that how this linear transformation goes for this. So T from R2 to R3. So this is the vector space from R2 to R3. Define as T of AB, this equal to AB 2 into AB. Clear? So this is the vector space from Rm to Rm where n equal to 2 and m equal to 3 and T of AB is defined. Is this transformation as a linear or not? Okay, so for this same concept as this, which we have to use in our generalized vector space 3 from V to W. Okay, so we have to check out that is this satisfy the additive property and homogeneous property. For this, let two vectors in R2 A, B, C, D are two vectors in R2. Okay, then T of AB. So by definition of a transformation, T of AB can be written as AB to AB, and T of CD can be written as CD and twice time CD. Clear? Now I have to check out that AB, CD, as R2 is a vector space, their addition AB plus CD and transformation of AB plus CD can be written as transformation of AB plus transformation of CD. So first of all, I have to find out this AB plus CD. So coordination wise addition A plus C, B plus D. So this is the addition of these two vectors in R2. Now the transformation of this. So how I define this transformation? Transformation of A plus C and B plus D. See this transformation of AB plus CD, which is nothing but transformation of A plus C, B plus D. So how you define this? This is equal to nothing but A plus C, B plus D, first coordinate, second coordinate, plus twice time multiplication of this two coordination. Say this. First coordinate A plus C as it is, second coordinate B plus D, and twice time of multiplication of this two coordinate A plus C and B plus D. Now I can simplify this. So this can be written as A plus C, B plus D, and twice time multiplication of this AB, AD, BC, BD. Okay. Now what I have to check out that T of AB plus T of CD. Clear? What is T of AB? AB and 2AB plus T of CD, CD and 2CD. So now is this T of AB plus T of CB is equal to T of A plus C, B plus D. So this can be written as this way. Addition of this two, A plus C, B plus D, A plus C and B plus D, and twice time AB plus CD. Now I have to check out that this equation is equal to this equation. So first coordinate it is okay, second coordinate okay, but third coordinate, what is the third coordinate? Twice time AB plus twice time AD. But where is AD here? There is no AD. Clear? So these two are not equal. So this is transformation of A plus C, B plus D is not equal to the transformation of AB plus transformation of CD. So for this, the transformation is not a linear transformation. Clear? So again we have to check out this two condition and we have to derive that this doesn't possess the additive property. So it is not a linear transformation. But suppose I can make, okay, the same example can be done by this also. How this? Because you know that R2. What is the basis for R2? 1, 0 and 0, 1. This is the basis for R2. So you can take the particular example for this and which doesn't satisfy for this. So this is 1, 0 and 0, 1 are the basis for this R2. And you have to check out this transformation of 1, 0, transformation of 0, 1 and transformation of addition of this two 1, 0 and 0, 1. Are they equal or not? So particular example we can check out for this. Suppose T of 1, 0. By definition T of 1, 0, T of AB can be written as A, B and 2 of AB. So this is A and B. So this is 1, 0 and multiplication of twice time multiplication of this two element. So this is 0. Clear? Same thing T of 0, 1, 0, 1 and twice time multiplication of this two coordinate. So this is equal to 0. So T of 1, 0 is 1, 0, 0 and T of 0, 1 is 0, 1, 0. Now 1, 0 plus 0, 1. 1, 0 plus 0, 1. This can be written as 1, 1. Now I have to find out the transformation for this. T of 1, 1. What is T of 1, 1? Say this. T of 1, 1. 1, 1 and twice time multiplication of this two element, which is equal to 2. So T of 1, 1 equal to 1, 1, 2 and T of 1, 0, 1, 0, 0, T of 0, 1, 0, 1, 0. So this is T of 1, 0 plus T of 0, 1, which is equal to addition of this 1, 0, 0 and 0, 1, 0. So this is equal to 1, 1, 0. But what is this? T of 1, 1? 1, 1, 2. Both are not equal. This is not equal to this. So this transformation is not a linear transformation. So whenever you have to show that the transformation is not linear, then you can give the particular example also. Using this particular example, you can show that if it is not satisfied, then the transformation is not a linear transformation. Now, suppose same example, but I can change the third coordinate. So T from R2 to R3. Then another transformation I have to define from R2 to R3, vector space R2 to R3 as T of AB equal to AB0. Okay. Then is it linear transformation or not? The method is same, but I can introduce the new transformation with AB and 0. The third coordinate will be 0. So I can find out this T of AB. So for this I can use this additive property and homogeneous property. So for additive property, what I have to taking this? Let AB and CD are two vectors in R2. So I can take this two vectors. So their image T of AB is AB0 and T of CD equal to CD0. Clear? So this is T of AB, which is AB0, transformation of AB, and transformation of CD is CD0. Clear? Now what I have to find out? This addition of this two vectors AB and CD, so which is equal to A plus C and B plus D. So this is AB plus CD, coordination of this A plus C and B plus D. Now again I have to find out this A plus C plus B plus D. What is the transformation for this? So this is the transformation of AB plus CD, and this is also written as T of A plus C and B plus D. What is the transformation? Yes, you know that. This is A plus C, B plus D and 0. Now this A plus C, B plus D and 0. Clear? Now I have to check out that is this equal to T of A plus C plus T of B plus D. Clear? So for this T of AB plus T of CD. How I check out this? T of AB, I know that this is AB0 and T of CD, which is equal to CD0. Clear? So this is A plus C, B plus D and 0. So this is A plus C, B plus D, 0. Now you have to look out that. So this is the last equation with the second equation, A plus C, B plus D, 0. So you must write that T of A plus C, B plus D can be written as T of AB plus T of CD. So this satisfies the additive property. So the first condition for the linear transformation is satisfied. Clear? And same thing, I can check out my last condition. T of C into, okay, K is any scalar. T of K into AB can be written as K into T of AD. So this is also some small condition, simple. T of AB, AB0, I can multiply this with scalar. K, KA, KB. So what happened that KA, KB and 0. So I can take K outside, K into AB0. Clear? So this can be written as K into T of AB. Clear? So this transformation is a possess the homogeneous property. So these two conditions are satisfied. So this transformation is said to be the linear transformation. Suppose now onwards, what we have to do this, we are given that the transformation and we have to find out that, check out that is the transformation is a linear or not. But now in some cases the basis is given and their images is given. From this you can evaluate your linear transformation. Okay, suppose this S V1 V2 V3 of R3, this is the basis for R3, and the given the value is V1 V2 and V3, where V1 equal to 1 1 1, V2 equal to 1 1 0 and V3 equal to 1 0 0. These are the bases of R3, and I have to define the transformation T from R3 to R2. Okay, but I don't know the transformation. What is the transformation? Okay, so you have to evaluate the transformation using the images of the vectors V1 V2 V3. So this only we know that this T is a linear transformation. T from R3 to R2, for which image of this T of V1 is nothing but 1 0, T of V2, this is your V2, and this is 2 minus 1, and T of V3 which is 4 3. So now what happened that you know that your transformation is T from R3 to R2, and you know that the basis for R3 is given. So this is, and you know that what is the basis. Okay, so we span the vector space R3. So this is V1, V2 and V3 are the basis for R3, and you know that also know that this transformation image of the basis under this transformation. So T of V1 you know that, T of V2 also know that, and T of V3. So you have three things. You know that your transformation is a linear, you know that the basis for this R3, and you know that the image of basis in this R2. Okay, so using these three things you have to evaluate that what is my transformation. Okay, so how you do this? So to evaluate the transformation using images, first of all you can check out that this is your basis. So any vectors in R3 can be written as a linear combination of these three vectors. Okay, this is the fundamental thing for basis. If any vector in the vector space, you can express as a linear, any vector in this vector space as a linear combination of its basis element. Okay, so suppose I can take this. So moreover you have to find out the linear transformation and also find the image of 2 minus 3 5. Okay, so this is the extra thing which you have to find out this. So any vector in R3 can be expressed as a linear combination of this basis. Clear? So suppose I can take this vector x1, x2 and x3, and as v1, v2, v3 are the bases, this vector can be written as a linear combination of these three vectors v1, v2, v3. So this is c1 v1 plus c2 v2 plus c3 v3. Clear? So where c1, c2 and c3 are the scalars. So now you have, this is the linear combination of the bases, and this is the any vector x1, x2, x3. Now how I find out this? I know the image of v1, which I have to put down this 1 1 1. v2, this is basis v1 1 1 1, v2 1 1 0 and v3 1 0 0. So this is nothing but this is c1 plus c2 plus c3 equal to x1. This is the first condition. Second thing, c1 this coordinate plus c2 and c3 is 0. So c1 plus c2 equal to x2. Clear? And the last thing, c1, c2 is 0 and c3 is also 0. c1, c2, c. Okay, so c1 equal to x3. So you can compare the coordination, first coordinate with the first and second with the second, third with third. So from this I have three equations, C1 plus C2 plus C3 equal to X1, and C1 plus C2 equal to X2, and C1 equal to X3. Clear? So this, you got the one value. C1 can be written as X3. You can put down this value into this equation. So this is the back substitution which you have to learn in your first chapter, linear system. So this is the linear system, three variables. C1, you can put down this values of C1. So C2 can be written as X2 minus X3. So you have a value of C1 and C2. Now you can put down this value C1, C2 into first equation, C1 and C2. So you get the value of C3. Now say this, what is the value of C1, C2, C3? C1 equal to X3, C2 equal to X2 minus X3, and C2 equal to X1 minus X2. So I can put down these values into the main equation. Say this, X1, X2 and X3. How you write this? Because this is my C1, X3, C2, X2 minus X3, and C3, X1 minus X2. So any vector can be written as this way of R3 as a linear combination of vectors V1, V2, V3. Now how you evaluate your transformation? Clear? Now you can expand your vector as a linear combination of the basis element. So I can take the transformation on both the side. Say this. Now taking the linear transformation on both the side. Both the side you have to take the linear transformation. T of x1, x2, x3, x3, t of 1, 1, 1 plus x2 minus x3, t of 1, 1, 0 plus x1 minus x3, t of 1, 0, 0. Okay. So this is your transformation. Taking t of x1, x2, x3, this is equal to x3, t of 1, 1, 1, x2 minus x3, t of 1, 1, 0 and plus x1 minus x2, t of 1, 0, 0. Clear? Now you know that this transformation of V1, what is the transformation of V1 is given in your question. Same thing, transformation of V2, which is t of 1, 1, 0, you know that, and t of V3, the transformation of V3, again you know that. Now you can put down these values into this equation, t of V1, t of V2 and t of V3. Then what happens? Say this. So t of V1, which is your 1, 0, t of V2, which is 2 minus 1, and t of V3, which is equal to 4, 3. So now you get this coordinate 1, 0, 2 minus 1 and 4, 3. Now you can simplify this. Okay. Whenever you have to simplify this, which is equal to 4x minus 2x2 minus x3 and 3x1 minus 4x2 plus x3. Clear? Which is nothing but which is your linear transformation t from R3 to R2, which have this type of images of V1, V2 and V3. So the simplest thing you have to do in your example. Now we have to find out this, what is the image of this 2, minus 3 and 5. Okay. So for this I have to put down this x1 equal to 2 here, x2 equal to minus 3 here, x3 equal to 5. And same thing 3x1, which is x1 is 2, x2 is minus 3 and x3 is 5, and which is nothing but 9 in 9, 23. Clear? So in this type you have to find out your linear transformation where only the image of the basis is given. Now you can find out or not. Okay, let's try another example. Suppose I were to find out the linear transformation when this only the basis is given and image of the basis is given. So consider the basis S equal to V1, V2 of R2, where V1 is given that 1, 2, V2 is given that 2, 3. Clear? 1, 2 and 2, 3. This is my basis for R2. And I have to define the linear transformation T from R2 to P2, Clear? So basis is given for vector space R2, and transformation is linear transformation from R2 to P2, set of all the polynomials of order 2, for which the image of TV1 is given that 2 minus 3x plus x square. Clear? So which is 2 minus 3x plus x square, the image of this element of the basis V1. Same thing, transformation of V2 is nothing but 1 minus x square. Keep in mind that the transformation is linear, this is the basis, and the transformation is defined from the vector space R2 to vector space P2. Clear? And considering the image of V1 and V2 is this. Now I have to find out my transformation. What is my transformation? So now do this. So what is the first thing you have to do this in? Yes, you know that this 2 are the bases for R2. So any vector in R2 can be expressed as a linear combination of V1, V2. So this is the fundamental thing, okay? Because you know that the basis and any vector space can be spanned by its basis, okay? So you can express any element of R2 can be linear combination of V1 and V2. Clear? So you have to find out the linear transformation, also find out some of the image, also find the image of this minus 1, 2. Okay, so let's try. Now this is the basis for R2. As we have said that in previous example, R2 is a vector space and any vector in R2 can be expressed as a linear combination of this basis. Okay, so this is your basis, and so I will take any element for this R2. Suppose AB. Okay, V equal to AB. Clear? V equal to AB, any element of R2. Now you have to take this arbitrary element of R2, and as said previously that this bases are V1 and V2, so AB can be expressed as a linear combination of V1, V2. Clear? So this C1 and C2 are the scalars, and any vector can be written as C1 V1 plus C2 V2. Clear? So AB equal to C1, what is your V1? 1, 2 plus C2, 2, 3. Okay. So what is your equation? C1 plus 2C2 and C1, 2C1 plus 3C2. So this is equal to C1 plus 2C2 equal to A. This is first equation, and C1 plus 3C2 equal to B. So comparing this coordinate, first with first and second with second. Okay. Say this equation. So to solve this equation, C1 plus 2C2 equal to A and C1 plus 3C2 equal to B, and we have to find out this solution like this. C1 equal to 3A minus 2B and C2 equal to minus A plus B. Clear? So this two multiplication C1 and C2 with vectors V1 and V2 gives the any element in R2. So this is V can be written as any vector 3A minus 2B V1 plus minus A plus B V2. So this is my combination, linear combination, and this is my coefficient. Okay. Now what happened that the next stage is I have to take the linear transformation. Okay. So I have to take the linear transformation T on the both the side. So how I take this? T of V equal to 3A minus 2B T of V1 and minus A plus B T of V2. Clear? So this is T of V1. I can put down these values of T of V1 here, T of V2. Clear? See this. So this is my T of V. T of AB can be written as 3A minus 2B and T of V1. So t minus 3x plus x square. Okay, this bracket is closed, plus minus a plus b and t of v2, which is equal to 1 minus x square. Now simplify this, because how you simplify this? Constant terms of x square. So this can be written as 6a minus 4b plus b minus a plus 9a plus 6bx plus 3a minus 2b minus b plus a into x square. Now equal terms you can add it or subtract. So this is a and this a, b and b, same thing. This is okay, a, b, b. So what is the simplification? So t of ab is nothing but 5a minus 3b plus minus 9a plus 6b x plus 4a minus 3b x square. So this is my linear transformation, comes from the vector basis v1 and v2 for the transformation t from r2 to p2. Now again I have to find out the image of this vector t of minus 1, 2. So I can put down this a equal to minus 1 and b equal to 2 in this equation, and with what I will get, that minus 11 plus 21x minus 10x square. Clear? Okay student, in this chapter, in second lecture, what we have to do this, we have done that how we evaluate the linear transformation. Okay, because in our previous first lecture we have to check out that the transformation is a linear or not, but in this second lecture we have to done the properties of the linear transformation and how we evaluate the linear transformation from the given image and given basis. Okay, in our third lecture we have to find the kernel and range of a transformation, and then one-to-one transformation and its properties for this linear transformation. So some of the basic theorems, and then isomorphism, and then matrix associated to the linear transformation. Okay, thank you.